We now move on to the mainframe systems, and I invite Mr. Naval Gund, who was the right-hand person for the project director in getting everything done, bringing things together, and talking to the scientific community to get things done completely. So we'll hear from Naval Gund on the challenges he faced.
Good afternoon to all. Thank you, Dr. Shiv Kumar. You heard all about the payloads. So payloads also had a lot of restrictions. So the configuration of AstroSat goes on the constraints of the payloads and some constraints from the subsystems. So configuration starts from the FOV requirement of all the payloads and sensors and antennas, and then the multi-spectral observations of the payloads needs the co-alignment of the 4 of the payloads, like SXT, CZT, and then UV80 and LAX-PC, whereas SSM is this one. So we accommodated 4 payloads on the top deck, and the one more constraint was the thermal stability of the payloads, especially CZT and UV80, thermal distortion. So because of their height, we decided to mount it at single plane. So both SXT and CZT were mounted on a single plane, and we took the structure from IRS 15K, and this structure was not sufficient. So we modified the structure to meet the mounting requirements and then the heaviness of the payloads. The total lift-off mass of the AstroSat is around 1,512 kg. Out of this, the payload mass itself is around 750 kg, more than that. So 50%. First time we were lifting such a heavy payloads on any IRS structure. So the structure needs to be reinforced so that it gives a good rigidity to the payloads and give a good frequencies for the payloads, so that there is no dynamic coupling between the structure and the payloads. The total, in addition to this, we had the requirement from the subsystems like the star sensor and all. So the mounting of the star sensors was to meet two heads of star sensor. The included angle between this mounting angle was around 110 degree. So we could achieve that. So without entering into the FOV of other payloads and this one, we could achieve the mounting requirement as required by the mission team. So then coming to the thermal part, this is a complex thermal requirement from the payload, because payload itself is having a lot of thermal constraints within the system itself. So it is a challenge to the thermal team that how to maintain the temperature for different parts of the payload, especially for the UV80 and then SXT. So we decided to have a good isolation from the main platform. So we use a titanium mounting adapter for the payload, for the UAT payload, and then single plane adapter for the SXT payload. And we introduced the titanium spacer between this satellite structure and the SXT payload, so that the thermal requirement are met. To tell you the complexity of this one, we have used around 800 to 900 heaters and 265 thermistors and around 65 numbers of fine thermal sensors. So this will tell you how much is the thermal design and thermal control is there for this AstroSat as a whole. Then coming to mechanisms, we had a mainframe mechanism, only solar panel is the mechanism. We had initially started with 3 panels to generate the power, but as the project continued, there was an increase into the power requirement both from the mainframe systems and from the payload. So because of that, we changed the type of solar cells used, and we reduced the number of panels from 3 to 2, and we used the multi-junction cell, because of which we gained around 5 kg of mass because of these changes. Then since we cannot get the power only from this one, we had used the lithium-ion batteries, 2 numbers of lithium batteries for this. So this is how the power systems work, and we have many converters to meet the voltage requirement from the different payload systems. Then coming to the AOCs and AOCE, we have 2 OBCs, ASIC-based OBCs and then it is 14 cards OBC. One is main and other is redundant OBC. And then the star sensor, the sensors includes the star sensor, then digital gyroscopes, and then the triaxial magnetometer. So these will form the sensors, and then the actuators are the wheels and the magnetic torquers. So this will form the actuators. So the OBC will have to provide the interfaces for all these sensors and the actuators requirements. Then coming to the payload data comes from the payloads, and then we have used the data handling system, and then the SSR capacity is around 200 GB. So once out of so many 14 orbits, for every 4 orbit, we used to fill around 144 GB of data, and there is no the instantaneous transfer of the data. It used to store in the SSR and then later playback whenever there is a visibility to this one. We had mounted 2 PAS, phased array antenna, to take care of which side of the earth the satellite comes, and then during that the respective phase antenna used to be used. Similarly, we had two chains of expand channels of 105 Mbps. So we could download downlink this one. We could download all the payload data through this chain link. Then coming to so actually we two main important aspects of the AstroSat is the exhaustive testing of the subsystems, payloads, and then the environment testing, and then the cleanliness contamination control. So we ensure that all the payload systems electrical interface testings was done for each of these subsystems like OBC, BDH, and RF system, and the full link was checked for each of the flight hardware system. So this ensured us there are no failures during our the ground checkout system. So this was exclusive and exhaustive testing done. This was done in 2 times. One is using the simulators, subsystems simulators were realized, and then using that we did. And then once the flight models of flight hardware came, we did with the flight model. So then coming to the environmental testing, we did the exhaustive testing for the EMIMC for all the hardware. All the hardware we did the EMIMC test so that there is no interference from one payload to other payload. That is made sure. And then the environmental testing like vibration and vibration acoustic. Anyway, for our mainframe systems, there was no requirement, but major part of the effort went into the qualification of the payloads. This was very challenging in the project. So you can see how the, for example, how the S60 payload is tested. It was hung in a 4-meter chamber, and then it was a separate exhaustive vibration fixtures and thermovac test fixtures were created both for the S60 payload and then on the U80 payload. So this is how we could qualify both on the engineering model and then the flight model. Then the main cleanliness requirement came from our PU80 payload. So we took the requirement from the U80 payload team. Accordingly, we followed the guidelines given by the committees and no stones unturned. See that there is no contamination happened because while it is in the clean room or during handling or during the transportation. At all stages, we could check the cleanliness and contamination. We used the MGF2 windows, and then the other mechanisms like during acoustic testing, during acoustic or thermal testing, we used the RGA, residual gas agencies, to see that any change in the contamination is happening. So luckily there was no change in contamination because of the advanced actions which was taken whenever the payload went into different parts of the laboratory. Then as a part of the contamination also, we have declared the part list and the process list, and as per that, we ensure that all the teams are follow this part list and process list. Then one more condition what we have put was all the flight hardware has to undergo baking. So we had discussed in the committee, and then each hardware, whether it's a subsystem or the payload team, payload hardware, it was baked for 96 hours for 70 degrees centigrade. So exhaustive baking was done to ensure that there is no contamination coming from the polymers being used in the satellite. So after the baking is over, we had put it in a nitrogen purged covers so that till it comes really for the integration, it is safely maintained, no contamination happening. Then even during the integration, we were thinking of putting one more container inside the clean room container inside the clean room. But luckily, we got a handle on the contamination control when the UAT payload came to for thermal testing in eyesight. So there we could see by consistently the mopping of the floor and the restricting the movement of the people, material, we could able to achieve some 8,000 cleanliness in this one, though the specification was 1 lakh. So from 1 lakh classroom, we could able to achieve around 7,000 or 8,000. So the requirement was around 10,000. We were well within that. So these were all the challenges we could able to overcome, and because of it, we are seeing the quality product in the space, and we are reaping the benefits from the satellite. Thank you.
May I now call upon Dr. Pandian to really tell us the challenges he faces, mission TPD. By the way, there was a 6th payload on AstroSat called CPM, the Charged Particle Monitor, with Professor Rao and the team at VSSC helped make. And Dr. Pandian was particularly worried about its role and its relevance for addressing SAA constraints. So maybe you talk about that.
Basically, AstroSat was a challenging project. I was not a mission person, but I was installed as a mission director by Dr. P.S. Goyal at that time. He had some kind of hope on me. So I had to work hard to meet these requirements. The first thing we faced from these payloads are the various requirements. So whenever I see professors, I get tremble. And all the professors who came, they demanded so many things. And every time they come out, we see a multi-wavelength space observatory, and they come out with so many requirements. Professor Tandon says 45-degree sun avoidance angle, and Professor K.P. Singh comes and says only 30-degree sun avoidance angle is good enough. Then later, we sat through something like 3-4 meetings and finally came out with that option of sun angle avoidance of 45 degree, avoidance of bright earth limb 12 degree, ram angle avoidance of 12 degree, moon angle of 20 degree. Apart from that, any bright object should not come into the field of view of any of this one. This is the initial this one. So much of constraints, and we have to understand their language, and I have to inform our spacecraft engineers and the spacecraft operation engineers how to put these things in the spacecraft so that all these things are met while operation. So that was the kind of thing to start with. Apart from that, we also had the star sensors which are mounted along the yaw axis. They have that 45 degree, 50 degree cone angle avoidance with respect to sun. So you have to have a 50 degree sun avoidance angle there. So if you see all these things put together, the language of scientists, how to put to the various DPDs of the spacecraft was very difficult for us. As a mission person, the work is, first I have to make them understand and then put those things in their subsystems, and it should work properly in the spacecraft, in the operations. So the language codifying has become a very major challenge, as our PD Koteshwar Rao told. This was the initial problem we faced most of the time. That was the challenge during the conceptual stage. Then comes the control challenges. See, control requirement, spacecraft orientation, pointing should be 0.05 degree, 0.03 degree is the goal. drift rate was very stringent. Then maximum satellite rate was given 4 degree per second, which means we had the reaction wheels which are of 5 Newton meter capacity, and the satellite is 1500 kg satellite, and you cannot have very high rates on that. So we had to limit that maximum satellite rate there. Then jitter is also very stringent here. This has to be met. But then came that 4 payloads are co-aligned about the positive roll axis, and one of the payload is about the y-axis, and it is rotating as SSM is rotating, and when it is rotating, Professor Tandon came and told, not at all possible. When UV-80 is viewing, the SSM cannot rotate. Then they came out with the step and stair idea. Not only that, how to compensate that motion in the spacecraft body. Then Jaswinder Singh came out with the SSM motion compensation algorithm and put it in this one, and then that part is taken care. Then the most important thing is that we have to worry about maneuvering the satellite, because it is a sun point, it's an inertial pointing satellite. One inertial pointing to another inertial pointing when it goes. 2 axes about which the sensitive payloads are mounted, apart from the star sensors. I have to avoid these 2 sides. 2 sides have to be avoided while rotating from one pointing to the another pointing. We have to think about a particular type of large angle maneuver, which is constrained about 2 of the axes. Then Koral and Juglikar team worked on that. Then we came out with a method of maneuvering in space without seeing the sun. Okay, one more minute. So that is the next, this one. Apart from that, this calibration exercise for the first 6 months, all the payloads have given a particular type of requirements. This was not easy to do on daily, day-to-day basis commanding. So in that process, what we did, all these requirements are taken and stored on board and pointing in the about one of the payload. If you point it, then it will complete this one in one go. Like that we have managed it. So this is one of the challenge we faced, and we managed this one. Apart from that, anyway, Naval Gund has told that BDH design was not the usual one. It has to be redesigned in order to meet all the requirements of the payload. Then similarly SSR also. Thermal heaters, number of heaters, 133 heaters and 252 temperature sensors have to be installed. Apart from that, filter wheel drive mechanism had 3 types of filters, FUV, NUV, and 5, this one, which means 7 into 7, 14 plus 5, 19 filters had to be changed during the operation. So all these things have been put together, and we made AstroSat ground segment packages and interfaces. Something like 2-3 years we have discussed. And in that Astro Viewer package, which we made it, then APPS, this AstroSat proposal processing system by Ayuka and all the professors, they made that software. Apart from that, flight dynamics modules, Astral and ASAT, mission planning, command sequence generation software, which was not easy because each payload has to be given a particular type of importance, and accordingly it has to be sequenced. All these things have taken place. And these ground segment meetings took place with hundreds of engineers and PAs of the payloads together, and we came out with the data processing, level 0, level 1 software, archival and retrieval software, and a growing MCAP database. One of the young scientists from mission came out with that idea, and they all put together. Today it is working for 10 years. I believe that all this effort has really helped in making the satellite work for this many years, and it is producing very good results. I thank the administration who allowed me to be the DPD mission for this one. I wanted to thank some of my colleagues like Koral and Juglikar for control, then Leo and team from operation from ISTRAC, they have taken wonderful care of the satellite. And Nagamani and Dakshayani, who has given me 200% support from the flight dynamics. And this was a very good experience I had. I really enjoyed the challenge. Thank you very much.
May now call upon our earlier program director and person in charge of mechanisms on AstroSat. You already heard there were numerous mechanisms on AstroSat. So, Nagesh,
good afternoon. I thank the organizers for making me a part of this historic occasion. I'll be speaking on behalf of mechanisms. Now, as far as AstroSat mechanisms is concerned, just a very brief overview, which most of you have already heard. This is the stout configuration. In the stout configuration, you can see that UVIT has 2 doors and SXT has 1 door, and we have, and we have 2 panels on either side. That is the solar array, that makes the solar array, and we have the SSM mechanism on this side, which is supposed to be steered by plus minus 175 degrees. Now, as far as the challenges are concerned, the UV telescope cover mechanism was totally new. The SXT mechanism was also new. The SSM mechanism was also new. As far as the array is concerned, this was modified with respect to our standard 3-panel array used in IRS satellites. Now, coming to the design requirements and challenges, as far as the telescope cover mechanism is concerned, this cover is supposed to ensure that there are no contaminants or volatiles which enter into the telescope payload, say in ground and maybe around 60 to 70 days after launch. And this cover is supposed to act as a sun shield in case of UVIT. And as far as SXT is concerned, the cover opens by around 275 degrees. Now, because of the presence of optics in these telescopes, we were not supposed to use pyro devices, which is our standard release mechanism. So we had to think of some new release mechanism, which is supposed to release the hold down from the doors. So we thought of 2-3 mechanisms, and then we finally we selected the paraffin actuator, which does not produce much shock. Now, as far as this particular paraffin actuator is concerned, because it's a new development, our management initially insisted that we have some imported ones as a backup. Now, in parallelly, we were developing this paraffin actuator. In one of the meetings, I remember our project director told that once you have got the imported, you will not definitely continue with the indigenous development. But in fact, we promised him we will use the indigenous one only on these telescopes, and I'm happy that we have used the indigenously developed paraffin actuators. It had to undergo rigorous qualification tests. Now, coming to the other challenges where the materials that we use on these mechanisms, they had to be, there was stringent contamination specification and control, which we had to ensure by proper material selection, then cleaning procedures, baking, etc. Here, between the door and the interface ring, we had to have a material, the TML and CVCM of which is 1 order better than what we use in our mechanisms. So we came out with a new material called as Tektron, which we qualified for these particular levels. Then the other challenge was, initially we had done a rough exercise in order to arrive at the design loads, and we had arrived to around 50 to 60 G type of load on the doors. The doors are nearly at a distance of 2 meters from the interface on this slender telescope. So when we did a qualification test, we saw that the hinges failed during the qualification test. This was really surprising because according to design calculation, it is supposed to withstand around 50 to 60 G. But upon close observation, what we saw was during the vibration test, the doors were going into a breathing mode, wherein in the middle it was lifting up and all the lateral loads were coming on the hinges. The hinges were not designed for the lateral load, the hinges were supposed to take only the out of plane load. So then we did a detailed analysis, and then we came out with a configuration which could withstand around 120 to 120 G. That is as far as the SXT is concerned. As far as UVT and SXT is concerned, as far as the sky scanning mechanism is concerned, here we were supposed to have an oscillating mechanism which is supposed to move by plus minus 175 degrees. Now, because there is no crossover, we thought we will not use slip rings, and we thought of a different type of mechanism wherein we could avoid the slip rings. However, there were nearly 200 plus power lines and the signal lines which we had to ensure that it does not provide much restraint for this oscillation. This is a new development. Okay, now coming to the lessons that we have learned, this is actually our initial configuration of the door. We had used tape springs and we had used hinges, and the one, that blue one there, that is that interface seal made of Tectron material, and we have the hold down mechanism. So as I already told, we had the failure of the hinges because the levels were very high. They were around 100 to 120 G. Then we changed the material from aluminum to titanium. Now, as far as the hinges were concerned, they could withstand the load, but we saw that because of rigorous chatter at the hold down point, we saw that, yeah, right, sir. We saw that the hold down spacer, there was a fusion because of chatter. This is called as fretting. So we had to replace that material, and surprisingly, there was one more issue at the hinges, wherein a Delrin spacer, we saw that it had got deformed. Again, this was also because of severe chatter. So for that purpose, we introduced a lateral restraint at the hinges. In fact, these were the, and another surprise was the same tape spring was used during this qualification test, and we saw some tear of this tape spring also. So that also we replaced with torsion springs. So these were the surprises that we had. The main lesson learned here is a detailed response analysis simulating the entire system is to be carried out to estimate the design loads, and we should never use two non-metallic components in contact with each other. This is something which we have got to ensure that we avoid. In fact, but for the first one, the other things were really surprising. The first one, of course, was it was actually a wrong calculation on our part, which we had missed initially. Coming to SSM mechanism, this figure shows the SSM payload on the SSM platform, and this is supposed to scan by plus minus 175 degrees. Here the main issue was, which we noticed at the flight model stage, was that the clearances between the rotating SSM and the adjacent systems, they were very small. Maybe in some cases it was hardly 5 mm or so. So we had to really rework on the MLI and reroute the harnesses, etc., in order to ensure adequate clearance. This was at the flight model level. And another difficulty we had here was to reach the SSM for assembly and integration and to carry out the test. We have got to really operate at this height with all these dresses and with the restriction on the number of people. So here the lessons that we learned was the moving appendages to have a slightly larger stay-out zone, that is a dynamic envelope to be liberal to account for the harness and MLI, and probably we should have thought of a better platform for the purpose of assembly and tests. Okay, thank you.
May I call upon Dr. Krishnamurthy to really tell us about optics?
Good afternoon, everybody. It's a great privilege for me to stand in front of great luminaries on behalf of my UEIT optics team at LEOS. I'm thankful to Dr. Alex and Koteshwara sir, who are my bosses. So in front of them I am speaking again whatever they have covered. So I just want to say our experiences in developing the UEIT optics. Next slide. Yeah. So this is the basically these are the two mirrors, primary mirror and secondary mirror. So the mandate already Professor Srinivasan sir has explained how the mandate has come to LEOs to develop these mirrors. So when it was awarded to us, the mandate was to develop these two mirrors and fabricate and test them at 633 nanometer. So because our experience was more of at 633 nanometers only. So far our heritage at LEOs was to develop the mirrors of Cartosat 2, Cartosat 1, and we have characterized it at 633. But now, so we could easily feel that yes, we could deliver. But over the period of development process, the mandate has changed to, we have to characterize them at 130 nanometer FU wavelengths. If it would have been 633 nanometer, only the mirrors, it could have been very easily done, because that was our experience, because we have done so many mirrors in the LEOs for Cartosat 2, Cartosat 1. But these mirrors now have to be developed for 130 nanometer. So first initially what we have tried is, we will develop these mirrors for 633 nanometer, characterize everything at 633 nanometer in air, and then we develop the methodology and test benches to characterize these mirrors at 130 nanometer. So that was our journey. So in the process, see, we the specification what I told, this is lambda by 60 nanometer, lambda by 60 RMS surface figure has to be achieved in space. But we are testing these mirrors in ground. So due to the gravity induced deflections, self-weight deflections, the surface figure whatever we have fabricated will not be 100% valid to the in-space conditions. So we have to characterize the zero-G effect on these large size mirrors. This we have done for 633, but now we have to do the same thing in 130 nanometer. So for this what we have done, we have developed the vacuum test bench, as Professor Dr. Alex explained in detail. I am thankful to him, he has already covered most of the things. It will be easy for me to now extend the discussion. So we have developed the UV80 facility. So for normally in the air, we need an interferometer. We have an interferometer like a Zygo interferometer. So standard interferometers are there. So you test the optics with null lens or CGH and characterize the aspheric surfaces. But now for this mirror, we don't have any interferometer at 130 nanometer wavelengths. So we have to have a collimator bench. So the collimator bench, again, there is no standard supplier to such a collimator to give. So what we have thought is, why not we use the same telescope itself as one of the telescope as a collimator and use the source. So what we have done, we have built a vacuum test bench. I'll show you here, sir. We have done the vacuum test bench. So we have converted one of the UV primary mirror and secondary mirror as a telescope structure. So we made the collimator, and this we have purchased, everything is a COTS item. We have not designed, specifically asked for anything. For example, we have purchased Hemamatsu photomultiplate tubes, and from Acton Research we have purchased the monochromator, and from Newport we have purchased the XYZ stages, and from Image Science we have purchased a chopper, and many things we have purchased and interfaced ourselves, because this test bench was not very difficult to be configured by any external party. We tried 3-4 external parties like a SAGM and other CESO, but nobody has come forward to develop this type of test facility for us. So then we have taken the challenge to develop ourselves at LEOs under the guidance of Dr. Alex and Koteshwara sir. And of course, I have to say that at every stage, Professor Standen sir has guided us, and he was the instrumental to guide and to teach us what we have to do at every stage. So we have done this total vacuum test facility. So the collimator we have used, the source we have used from the Shimadju, yes sir. And then UV source, Acton research monochromator we have used, and we have tested this. So we have taken the detector from the collimator. The source is coming, the collimated 380 mm diameter mirror beam is coming, and we have plotted the PSF from the actual test image, actual telescope. So the PSF, theoretical PSF we have calculated from the Zmax, and how much it should be at every wavelength, and we have calculated, and we have done this PSF values in vacuum. So we have done this at 130 nanometer, 150 nanometer, and 220 nanometer. At all the UV wavelengths we have done, and we have also done this test for 0G simulation of these wavelengths. So, and as Dr. Alex also told, so this transportation was also one of the very critical tasks, because contamination control is one of the major critical tasks. So coating people have done excellent job, but then we have to transport them to IAA. So we have made the two vacuum containers. So it is completely, we have done the vacuum, and then we have put both primary mirror and secondary mirror in each container along with the test coupons. So then we have carried it, and even now also they are in good condition to store other optical components in the thing. So this vacuum test facility is still there. So as Dr. Alex told, so this is one of the major challenge and major experience, and really it is even till today when I speak about vacuum test facility, I'll get so much excited. So I am thankful to my team. Yeah. So, sorry, sir. This is only, yeah. So thanks to and opportunity to present the LEO's challenges and experiences in developing the UVT optics and mirror assemblies. So on behalf of my entire UVIT team, I am really thankful, and I am thankful to organizers to give this opportunity to me. Thank you so much.
So with that, we sort of close this particular session, and I leave it to thanks to all the speakers, and I apologize for the short time that was given to everyone to really talk about their experiences.
First, let we give a big thanks to Dr. Srikumar for moderating this session.